In this video, we're going to take a further look at exponential growth, but we're going to use a formulaic approach. So here is just the generalized way that we can take a look at this. If a quantity starts at size p sub 0 or p naught, that will just be the way that we represent our initial population. And it grows by some percent written as a decimal. Remember, we're going to convert these to decimals. And we're going to use the letter lowercase r every time period. So if it starts somewhere, we have a growth rate. Then the quantity after n times periods, meaning some time period out in the future, can be determined using either of these relationships. Now, I will focus mostly on the explicit form, but recursively, this is the best way to start thinking about it. Is you have some population at some time. The way you figure it out is you take the previous one and then you multiply by 1 plus r. Now, remember from a previous video that this piece right here is known as our growth multiplier, not the growth rate. All right, I'll give you an example of what I mean. Let's say that our growth rate for a certain population is 5%. That would mean that R equals 0.05. Recall that we would do 5 divided by 100. But our growth multiplier then from this would be 1 plus 0.05 or 1.05. Okay, so those are two different things going on. The explicit form of this, this will take us to any year or any time period, is we would start with P naught, that's our starting value, multiply by the growth multiplier for some period of time. Okay, let's take a look at some specific examples of how to do this. In 2001, there were 100 inhabitants in a remote town. Population has increased by 3%. There's our growth rate every year. So I'm going to make a little note of that. Our growth rate is 3%. If we convert that to a decimal, which we always want to do, we divide by 100 and we get 0.03. Using this growth rate, predict how many residents there will be in the remote town in the year 2030. So your time elapsed is also very important. So we'll use the explicit form. And the reason I want to use the explicit form is because I don't want to calculate the growth in every single year along the way. I just want to jump from the year 2001 to 2030. So our explicit form is that our population at any state, here's the formula again, looks like this. Okay, so let's plug in what we know. Well, P naught is our original population, that's 100. Our growth rate, R, is given to us as 0.03. And then we're going to want n number of years from 2001 to 2030. So we would have to calculate that. Now, that's just simple subtraction. 2030 minus 2001 gives us 29 years, all right? So that would be a 29 up here. And we enter this into our calculator. You might want to go ahead and add 1 plus 0.03 first. You're going to enter this in. You definitely need a scientific calculator. If you're using a cell phone calculator, you can kind of turn it sideways to get this, but I recommend a scientific calculator or online scientific calculator if possible. Okay, so let's see. You're going to take 100 times 1.03 to the 29th power. I'm getting 235.656, but I'm going to round off to the nearest person because we're talking about people here. We would expect our population to be 236 people after 29 years. Still not that large, but it certainly has more than doubled. Take a look at another example. You can do the same thing with money. Now, this isn't really a population in the sense of people or animals, but it's sort of the same idea that your money is growing in the same fashion. Your money is getting populated. So in this example, Jake borrows $20,000 from the bank at an annual interest rate of 5.7%. That is our growth rate. Well, in this case, it's growth rate of his debt, so that's not necessarily a good thing. If we convert that by dividing by 100, we will find that R equals 0.057. That'll be key. Okay, that's going to be compounded annually. That just means we're going to apply a growth of 5.7 each year. Using the exponential growth formula, find the amount owed to the bank after 6 years. Okay, so looking at the formula, P sub 6 would be equal to P naught times 1 plus R to the n power. In this case, our original population, although it's money, our money is populated as 20,000. Our growth rate is 0.057, so 1 plus 0.057 is 1.057, and it says in the problem 6 years. So let's see what happens to the money. In this case, the debt. we're going to round off to the nearest cent. So I'm getting $27,892. Then it says 0.01689, but rounding off to the nearest penny, 0.02, all right, and 2 cents. So this is kind of bad, right? And Jake borrowed this much. Now it seems he owes this much. So that's what happens to our debt. Now, the flip of that is that if he was investing money at a 5.7% interest rate or rate, then that would be money earned rather than money owed. That's kind of how money works. Let's take a look at a couple other examples. These are a little more abstract. This one talks about a certain population that is experiencing exponential growth rate. And we're given two pieces of information, two data points. P naught equals 128 and P sub 1 equals 160. Okay, what is the growth multiplier? Well, notice that we're given the starting population and 1 year later, right? So it looks like this 128, 160, and so on, right? This is the sequence. Well, if there's a growth multiplier to get from here to here, right? If there's something that takes us from there to there, or multiplying by something, then we can use division to kind of figure out what that is, right? We would divide going backwards. So that means we can just take 160 and divide it by 128 and see what we get. On my calculator, I get that to be 1.25. So our growth multiplier, that's the first answer, is 1.25. Now remember that our growth rate, we can get that by looking at the growth multiplier. The growth multiplier was the 1 plus R. So if we want just the growth rate R, all we'll do is subtract 1 from that, and it's just 0.25. The third part says, write a model for the growth of the population after n years. So using our explicit formula from above, we would learn that P sub n is equal to P naught, 128, times 1 plus R, that's our growth multiplier, right here, 1 plus R, to the nth power. And then finally, the fourth one, you can use this model to find P sub 10, and that would just be a matter of plugging in 10. 128 times the growth multiplier 1.25 for 10 years. This is where you will always need that scientific calculator. I'm going to use mine as well. And I'm going to round this off, right, to 1,192. I'm going to use a whole number because we're talking about a population. So if I'm talking about people or animals, I'll always round off to the nearest whole number. Okay, now last problem is, what if the years aren't next to each other? We have to do a little more thinking. Okay, so here's another problem. In this problem, we're going to round to the nearest hundredth, 2 decimal places. A certain population is experiencing exponential growth rate such that P naught is 50. That's where we'll start. And P sub 15 is this decimal value, 273.678. Okay, and I know I'm using decimals here, but I'm using decimals for a reason, to show you how you can back calculate the growth rate. So here, I don't want to do something like, okay, P naught, P1, P2, P3, P4, all the way out to P15. I don't want to guess here, because if I know the first term is 50 and I don't really know what I'm multiplying by to get to 273.678, that's going to be very confusing to guess and check that. I'm like, I don't know what I'm multiplying by. So how can we do that? Well, we're going to use the growth model, a little bit of algebra, and our scientific calculator to figure that out. So we're going to be writing a model for the population growth. And to make that model, we're going to have to solve for the growth rate or the growth multiplier. Then we're going to use this model to find P sub 50. So this is kind of what it will look like. Remember in general that our formula is P sub n equals P naught times 1 plus R to the n power. Now we can use these two pieces of information. Here's the first one, P naught is 50. That just means in this formula, P naught would be equal to P naught times 1 plus R to the 0 power. Now all I did there is I just plugged in 0 for n in both places. We'll come back to what we do with that in just a second. Then I take the other piece of information, which is P sub 15, and I plug that in over here. I say, well, P sub 15, also plugging in for n, both places, is P naught times 1 plus R to the 15th power. I can use both of these at the same time to calculate R. Okay, so what we do, let's take a look at the one on the left over here, right? You might remember from algebra that any number raised to the 0 power, right? Any number raised to the 0 power is just equal to 1. So all of this really just goes to 1. And all we learned is that P naught is P naught. It's like, oh, well, duh. Now, the reason I went ahead and gave you that step is because possibly on another problem, we might not know what P naught is. We might have been given like P3, and we would have to have a piece of information there. Okay, let's take a look at the one on the right and see what we learn. We learned that P sub 15 is equal to P naught times 1 plus R to 15th power. All right. So in this case, let's go ahead and plug in P naught. It's 50. And let's go ahead and plug in P sub 15, which is given up here in the problem as 273.678. If we do our algebra would look like this. We divide both sides by 50. So calculator, 273.678 divided by 50. And do a little rounding as I go. I'm getting, but I'll round at the very end, 5.47356. And then these 50s will go away. We get 1 plus R to the 15th power. So here's the algebraic step that you may have forgotten, but I'll just show you. And you'll have to figure out where the buttons are on your calculator. So what we're trying to do is figure out what I can multiply by 15 times to get to that number. And the way that it's done is we use a 15th root. So the algebra step is to both sides of this equation, I'm going to take the 15th root. All right. What will happen on the right side is that the 15th root and the 15th power are inverse operations. In other words, those will cancel each other out, and you'll just be left with 1 plus R, which is really what we want. On the left side, this is something you'll need to figure out on your calculator. And there's several ways to do that. One is you might have a button that looks something like this. And this is basically any number, any root, and you're going to try and plug it in that fashion. The other possibility is you might only have just a power button that looks like this, which is called a caret, and you can raise it to the 1/15th power. So there's several ways to do this. You'll have to explore on your calculator, and you can certainly look online for there. So I'm going to go ahead and type this into my calculator to see what we get. And you can pause the video and try for yourself to see what you can get as well. Let's see. I'm getting it's 1.119999. Let's go ahead and round it off at this point to 2 decimal places. I'll just say that 1 plus R is about 1.12. There's a 9 back here, so we're going to round that up. Okay, so at this point, what we found is our growth multiplier. Almost done. So now we're ready to write our model. And our model will be population for any number of years is equal to P naught 1 plus R to the n. Let's plug in what we know. We know that P naught, original population, is 50. And now we have solved, with all of this work, for 1 plus R. It's 1.12 to the nth power. So to finalize this, the last question says find P sub 50. And now we're ready to do it. We can just plug in 50. So the population started at 50, our multiplier is 1.12 for 50 years. This also will require a scientific calculator. I'm going to go to mine, and I'm going to be rounding off this number to the, I'm going to use the nearest whole number since we're talking about a population, 14,450. Okay, I hope in this video you've learned a little bit more about how to use information to write an exponential model.